Imagine, right, taking like any photograph, a memory, just
Yeah.
frozen there in 2D, and boom, maybe soon you could step right into it. A full 3D world made from that one flat picture. You sent me this research, and wow, this kind of immersive experience, it might be closer than we think.
Yeah, that's exactly the kind of exciting territory this new work is exploring. You shared that paper outlining a method for generating these navigable 3D environments, and it's wild, starting with just a single static 2D image.
Yeah, stepping into a photo, it's definitely got that wow factor.
Yeah.
But the paper, it points out the obvious, right? Turning a flat image into a 3D world, it's not a walk in the park. There are some big challenges. I mean, think about it. So many different 3D scenes. They could all look like the same 2D image. So how do you, even begin to figure out what's hidden? How do you make sure that 3D space actually feels real, feels right?
Absolutely. That's the core issue they're tackling head on. It's not just about figuring out the depth, the spatial relationships that are missing in that 2D image. You've got to fill in the gaps, the stuff the camera couldn't see, and make it feel natural, like it belongs there, stylistically consistent. And this new method, they even call it a recipe, offers a really smart way to crack this problem.
I am really curious about this recipe and, what it could mean in the real world. The paper, it mentioned some really cool possibilities. Stepping inside a painting, new VR experiences, even changing how we interact, like in social apps, games. So what's the big idea here? What are we diving into today with this research?
Okay, so our mission for this deep dive is to unpack their approach. It's a two-pronged attack, and get this, they break down this super complex problem into two more manageable stages, and, well, a lot of times that leads to solutions that are more robust, more elegant.
I like the sound of that, breaking it down.
All right.
Okay, so let's hear it. What are these two key steps in their recipe for turning a flat picture into a 3D world we can explore?
All right, so step one, the first critical part is taking that single input image and they generate a complete 360-degree panorama from it, like unfolding the entire scene, a full spherical view. And then step two, they take this panorama and lift it, that's what they call it, into a 3D space that's refined and navigable. The paper actually says they're targeting VR experiences within, get this, a 2-meter cube. So you actually have a sense of the scale they're working with.
A 2-meter cube in VR. Yeah, you can totally picture moving around in that. All right, so let's unpack that first step. Creating a full 360 panorama from just one snapshot. How do they even begin to imagine and then fill in all that missing stuff, all the parts of the scene the original camera couldn't see?
This is where their approach gets really cool. They actually use existing AI models. These are models that are already really good at, and get ready for the technical term, inpainting. It basically means filling in those missing or damaged parts of an image. The real magic trick here is how they frame this as in-context learning. They're not training new models from scratch. They're cleverly using what these pre-trained models already know how to do.
I see. So they're using in-context learning, which is a fancy way of saying they're not teaching these AI models from the ground up. They're showing the model this single image and then saying, okay, based on this, now imagine the entire 360 view. It's like teaching by example in real time. But how do they make sure the AI isn't just making a random guess?
They use a method called progressive synthesis. Essentially, they generate a bunch of overlapping perspective views, and then they very carefully stitch those together to create the whole panorama. The paper actually talks about 3 different methods they experimented with for this progressive synthesis.
Okay, tell me about those different approaches. What worked well and what didn't really pan out?
The first one, they called it ad hoc, and it was pretty straightforward. They basically just told the AI, hey, create a panorama, instructions like equirectangular image, panorama. And the result, it kind of looked okay, but it had some issues with geometric distortion, especially in the sky and ground areas.
Okay, so asking the AI to just imagine the entire 360 in one shot seems like a tall order. What was the next approach?
The second one, they called it sequential. And with this, they actually simulated rotating a virtual camera, left, right from the original viewpoint, and then tried to fill in the sky and ground. So they figured, okay, the middle part of the panorama should be pretty accurate because it's close to what the original image showed. But, well, the ground often didn't line up right, and when they stitched all those different views together, you got these weird artifacts. And that's probably because the model didn't have a complete understanding of the whole scene.
I got you. It's like creating pieces of a puzzle without having the box to look at. What was the third method? The one that worked, the anchored method.
Right, so the anchored method, it's pretty clever. They started by duplicating the original input image and placing it on the back side of that panoramic sphere. So basically, they're giving the AI this initial context for generating the sky and the ground first. And then after they generate those, they get rid of the duplicated part, and then they start rotating the virtual camera, creating all the remaining views. By giving the model that initial anchor point, that global context, they got much more consistent equirectangular images. If you look at figure 3A in the paper, you really see the difference, the anchored result. It's so much more consistent.
I see. So giving the AI that initial context, even if it's just a duplicated image on the back, really helps it create a more consistent panorama. Now, the paper, it also talks about those prompts, right? The instructions you give to the AI. I can't imagine just saying generate a panorama is enough.
No, you hit the nail on the head. They actually found out pretty quickly that using simple image captions, like just describing the original photo, it wasn't very effective. The AI would just kind of duplicate stuff from the original image to fill the panorama, which looked really unnatural and repetitive. Figure 3B in the paper on the left, it shows this, you see the same main subject just repeated over and over.
Right, so just describing what's in the photo isn't enough for the AI to imagine what could be around it. So what did they try next?
They tried using more general descriptions, kind of a broader approach. That helped. It stopped the AI from just copying things directly, but they still ran into issues, especially with the sky and the ground. The AI would often make them like mirror the main scene in a weird way. You can see this in figure 3B on the right. It looks like the ground is just a reflection of what's right in front of you.
That sounds, well, pretty trippy. Not exactly the kind of environment you'd want to hang out in VR. So how did they finally get the prompting right, to get the results they were looking for?
All right, so they use this vision language model called Llama 3.2 Vision, and they give it three specific prompts. First one asks for a general description of the scene, the overall vibe, but specifically telling the AI to ignore the main stuff, like big objects or people. The other two prompts are directional, one focused on the sky, or the ceiling if it's indoors, and the other on the ground, or the floor. And get this, the AI, it can actually figure out if the scene is indoors or outdoors on its own, so it knows whether to create a sky or a ceiling and a ground or a floor. If you look back at figure 3A, that anchored method, you can really see how well these targeted prompts work. It creates a much more believable panorama.
That's clever, making the AI think about the overall mood first and then zero in on the sky and the ground separately. Now, I noticed they also do some refining after they create that initial panorama. What's involved there?
Right, so to make the image even better, they do something called partial denoising. They use another AI model, a text-to-image diffusion model, and think of it like using Photoshop to smooth out any rough edges or imperfections. But they only run it for a short time, like the last 30% of the process, so they don't mess up the overall structure. And they use a soft mask so the refined areas blend in really smoothly.
Gotcha. Okay, so they've created that 360 panorama. Now they need to lift it into a 3D space we can move around in. How do they add that depth, that feeling of actually being able to walk through the scene?
Well, they started with something called Metric 3D V2. It's a state-of-the-art depth estimation model. The idea was to render a few images from that generated panorama and have this model predict the depth maps. And those depth maps, you can combine those to create a 3D point cloud. But they ran into trouble. The point clouds, they were kind of distorted. Points would be too close or too far from the virtual camera. Figure 4A in the paper, it shows these distortions.
I bet. Distorted geometry would totally ruin the VR experience, so they needed a better way to estimate the depth.
Exactly. So they switched over to a different depth estimator called Moj. Now, Moj, it's got some cool technical stuff going on, but basically, it's really good at understanding depth, even if the image is like tilted or zoomed in. It's got these affine invariant properties. The only problem is the depth estimates from Moj, they're not metric, meaning they don't tell you the actual distances in real-world units. So what they did is they came up with a way to align Moj's depth scale with the metric scale they got from Metric 3D V2. They calculate a scaling factor based on the quantiles of the depth predictions from both models. And then they apply this scaling factor, this formula, to align the depth scales from the two different models. You can see it in equations 3 and 4 in the paper. It's a bit mathy, but it works.
They're basically combining the best of both depth estimators.
Yeah.
The robustness of Moji and the accuracy of Metric 3D V2. Clever. But even with depth information, I'm thinking there are going to be some areas that were hidden in the original photo, right? And those areas would still be empty in the 3D world. How do they fill those in?
All right, this is another really smart part. They handle these missing parts, these occluded areas, as another in-painting task. But this time, it's guided by rendered point clouds. So as you move that virtual camera around, areas that were hidden before, they become visible as holes in the rendered view.
I see. So the missing information, it creates a sort of mask, an outline, and they need to fill in what's behind it. But the paper says that regular in-painting models, they have trouble with the masks that come from point clouds. Why is that?
So the masks that regular in-painting models are trained on, they're usually nice and smooth, well-defined. But the masks you get from point clouds, especially when you're viewing the scene from new angles, they can be all fragmented, like scattered puzzle pieces. It's tough for a general in-painting model to figure out what it needs to recreate.
So they needed a model that could handle those kinds of fragmented masks, the ones made from point clouds?
Exactly. They fine-tuned an existing in-painting model called ControlNet specifically for this. And check this out, they only needed like 5,000 training iterations to get it to work well. That's pretty efficient.
And how do they create the training data for this? To train ControlNet to work with those fragmented masks.
They invented this, get ready for it, forward-backward warping strategy. So they take that initial point cloud, they project it to a new virtual camera view, and then they project it back to the original view. And what happens, because of things being hidden in the 3D scene, this creates masks in the original image. And the key here, because the warped points are already geometrically correct, the masks they make, those are accurate too. Really good guides for the in-painting model. Table 2 in the paper, it shows this big improvement in something called PSNR, peak signal to noise ratio, basically how good the generated image is compared to the target. And they get this by using their forward-backward warping strategy. It's clever, right? They created their own training data with this warping, so they don't need tons of label data.
That's ingenious. No need for all those manual annotations. Okay, so to make sure they can explore that 3D world from different angles, how did they choose those camera positions?
Yeah.
For generating those training views.
They created this whole grid of virtual camera poses incorporating rotation and translation, all inside that 2-meter cube. So they put virtual cameras at the center at each face of the cube, and at each of the 8 corners, that's 14 different positions. And then for each of those, they applied 14 different rotations, covering forward, back, left, right, up, down, and then those same directions with a 45-degree roll. So it's a lot of viewpoints, 14 times 14, to capture that scene from all angles.
Okay, so they have all these infilled views from a bunch of different camera poses. Now, how do they combine this into an actual 3D model, something you can experience in VR?
This is where they use something called Gaussian Splatting, or 3D-GS for short. They chose 3D-GS because it's known for creating really high-fidelity results. And get this, it can be rendered in real time, which is a must for a good VR experience. They use something called Splat Facto. It's an implementation from the Nerf Studio toolkit.
Right, Gaussian splatting. We've talked about that before. He uses those tiny 3D Gaussians, those little blobs of color and density, to represent the scene. And it renders really fast. So how do they create these Gaussian splats from those images and point clouds they generated?
That initial point cloud, the one they get from lifting the panorama into 3D, it's a really good starting point for the 3D-GS representation. And because they have this good starting point, they can train the 3D-GS model much faster, just 5,000 steps. And they even disable something called periodic opacity reset to speed things up even more.
Makes sense. A good starting point means less tweaking is needed. Now, what about those infilled areas? How do they combine the data from that point cloud conditioned in painting into this 3D-GS model?
They mainly use those images for the specific areas that were filled in. And for the rest of the scene, the parts from the original panorama, they use those images directly. They're basically taking advantage of everything they generated.
And they also mentioned something called a trainable image distortion mechanism. What's that all about?
This is their final touch, to make things look as good as possible. To take care of any little inconsistencies between the different images they created, they add this trainable image distortion model to the 3D-GS training. It's basically a small neural network that learns to slightly warp the rendered images. This warping, it helps to correct any misalignments, and the final results, they're much sharper, more detailed. You can see the equation for this process in the paper. It's equation 5 and figure 9. That shows you the difference it makes visually.
It's like adding that final layer of polish to make everything look super smooth and high quality. So they've built this whole system. How did they test it out? What kinds of images did they use, and what did they measure to see how well it worked?
Okay, so they tested it on different kinds of images. Real photographs from a data set called Tanks and Temples, and also synthetic images from World Labs. They actually list the specific names of the images they used from Tanks and Temples in Appendix A of the paper. And for evaluation, they used a bunch of different metrics. Clip-eye, that measures how well the rendered views from the 3D scene match the original image. And then they use several no-reference image quality metrics like neek, brisk, and q-align. These try to predict how good the image looks without needing a perfect original image for comparison.
So they can actually measure how closely the 3D world matches the original 2D image and how good the results look to the human eye. What did their results show for the panorama generation compared to other state-of-the-art methods?
Table 1 in the paper sums it up. Their method, it was better than two other advanced panorama generation techniques called MV diffusion and diffusion 360, better image quality, and a better match to the input image. MV diffusion had trouble with the sky and ground, and diffusion 360 often created images that were too saturated or had big areas with just one color and no detail. Their anchored approach, with those specific prompts, it created better panoramas overall.
So their strategy for generating panoramas, it really paid off. What about that point cloud conditioned inpainting stage? How did their forward-backward warping technique compare to other methods?
Table 2 in the paper has those results. The forward warping and the forward backward warping, they both did pretty well in terms of image quality, but that forward backward warping, it was much better at matching the input condition, those fragmented point cloud masks. It created more accurate, more faithful infilled regions.
And what about the whole 3D world generation pipeline? How did it stack up against other methods out there?
They compared their approach to Wonder Journey and Dimension X, which create videos from a single image. So they take those videos and use another tool called CUT3R to extract the 3D info. You can see some visual comparisons in Figure 6 in the paper. Wonder Journey, it sometimes created videos that weren't consistent, so it was hard to build a good 3D model. Dimension X, its videos were more consistent, but the 3D models lost detail. Table 3 has the numbers, and their pipeline consistently got the best scores for image quality. And their argument is, by doing things in two stages, first creating that good panorama, and then doing the point cloud inpainting, they avoid some of the problems that come with trying to create the 3D world all at once from a video.
Right, so by breaking it down into those two steps, they're using the best of both worlds. They also did an ablation study, right, to see how each part of their method contributes to the final result.
Yeah, Table 3 also shows those results. They compared their ControlNet inpainting with another method that uses a model called ViewCrafter to augment the point cloud data. ControlNet, it just worked better for creating the 3D model, and they also showed that their trainable grid distortion that makes things look even better, more detail.
So every part of their method, it's important for getting those awesome final results. Now, no research is perfect, right? What are some of the limitations, the challenges with this method?
They're honest about the limitations. One is the size of the navigable area. Right now, it's limited to that 2-meter cube. When you go beyond that, it becomes way harder to accurately fill in those areas that were hidden in the original image. And, filling in the backsides of objects or entire areas that were completely hidden, that's still really tough. And they also point out that you can't create the 3D world on the fly in real time yet. Those diffusion models, they're computationally expensive. But once you create that Gaussian Splatting model, it can be rendered in real time in VR.
So you can't instantly generate and explore a massive world, but that 2-meter cube, once it's made, it's smooth and interactive in VR.
Right.
That's still a big deal, right? Creating an immersive experience from a single image.
Totally. It's a trade-off between the computing power needed and the quality of the experience.
This has been a really cool deep dive into this research. So for anyone who just tuned in, the big takeaway here is these researchers have made this really innovative way to create immersive 3D worlds from a single 2D image. They combine existing AI techniques in this smart two-step process, first making a panorama and then lifting that into 3D using point cloud conditioned inpainting and Gaussian splatting.
Exactly. And the cool thing is, for someone like you who's all about staying ahead of the curve, this method, it doesn't need a lot of extra AI training. It uses the power of models that already exist.
It's like they found a shortcut to creating these immersive worlds by being strategic about how they use the AI tools that are already out there. Makes you think about what's possible. What if they could overcome those limitations? Imagine instantly creating and exploring anything from a photo, historical sites, imaginary worlds. What could we do with that kind of technology? That's something to ponder even after today's deep dive, right?
Definitely. The potential is huge, and this research gives us a glimpse of what the future could hold, maybe even sooner than we think.